Now we shall calculate the design wind pressure, and if we are talking about let us say the title, we are talking about the loading along the, we can say, y direction itself. So along the y direction, we can say that if we are applying the or calculating loading along this particular direction, we are talking about the body axis. So first of all, if you're talking about the like serviceability load case, so we do have this formula that is 0.6 into V design theta square multiplied with CSHP and multiplied with C dyne. So in our case, the value comes out to be 48.23, and the value of CSHP we can take it as 1.54, and C dyne again we can take it as 1. The value comes out to be 2.15 kPa, and that shall be the wind load along the y direction. So first of all, if you're talking about the sorry the now if you're talking about the calculation of the wind load, so we do need to understand that if we're talking about the calculation of wind load along this axis, so if we draw this in plan view, so this shall look something like this, the I shape section, and we are calculating the wind load along this particular direction. So we have to consider this particular dimension for calculation of the wind load. Similarly, if you're talking about the, let us say, other dimensions, let us say this particular case, that is the beam itself, or all of these beams. Now, all of these beams look something like this. So we are calculating or applying the wind load along this particular direction. So the dimension that needs to be considered is the height of this steel beam, that is 360 mm. So that is why we have considered the dimension for all of these we can say individual structural steel sections. That is for the steel columns, it shall be different. For steel beams, it shall be different. For bracing, it shall be different. So we have to apply the UDL on all of these members, and obviously we do have this in kPa, that is kN per meter square. So we have to multiply it with the affected dimension that on which we have to apply the wind load. So we can for 360 mm, when we multiply with 2.15, it gives us 0.774 kN per running meter. So in all of these structural steel members, we have to apply the UDL of 0.774, obviously for the serviceability. So before we proceed further, I shall apply this wind load so that you shall get more understanding of how and why it is getting calculated. So 0.7744 for 360 mm. So we can go to the elevation view here, and an elevation view can go to either one, or what we can do is that again we can go to the plan view here, level 1, apply, display undeformed shape, and we can select all stories option here, and we can go to the view, show selected objects only, again go to the 3D view. So now here we can again select the one story option here, and the wind load that we were calculating for 360 mm was 0.774 kilonewton per meter. So in all of these members here, what we can do is that we can go to the control and W option, object assignment, can click on the this section. Yeah, so now we can see what size of member we are right now facing. So we can select all of these members here, and this is also like 360 UB 44.7. So we can go to the assigned, frame loads and distributed. The direction of the loading shall be along Y. So we can click on this WLY and serviceability. The value shall be 0.774 kN per running meter. It shall be along the Y direction. So we can click on, sorry, the direction is not gravity. We just need to undo the application. Again, we do need to select all of these members here. We can click on this direction load application shall be global Y, and replace existing load 0.774 kN per running meter here. So now this is correct that we have to apply the wind load on all of these members here. It is basically along the Y direction and serviceability. Similarly, for surface dimension of 230 mm, it is approximately 0.495 kN per running meter. So 230 mm is basically this particular dimension for 530 UB 530/82. So if we go to the define section, properties and frame section, if we double click on 530 UB82, that is a column size already considered here. So this value, we can say that flange width is approximately 209 mm. So we have considered that on the conservative side only. So we can apply 0.495 kN per running meter on all of the, we can say, vertical members here. So we can select all of these members here, all the columns that we are considering. We can click on the global Y itself, and instead of 0.774, we do need to consider 0.495 kN per running meter. So again, we can click on the apply. So now the wind load has been considered on the columns also. And the thing is that, we have to consider that the we on all of the structural steel sections, because of the wind property and because of the weakened surface characteristic, the wind load shall be applicable. So for all of the structural steel members, we have to apply. And the most important thing is that after designing these structural steel sections, if we have to increase the size of this member, again we have to repeat the whole process of the calculation and apply the UDL on all of each and every one of these members. After that, if you're talking about surface dimension of 200 mm, it is approximately 0.43. And so surface dimension of 200 mm is applicable for this bracing arrangement here. So we can click on the Control Shift A option and we can select these members here. So we can apply 0.43 kN per running meter on these members here. And after that, if we are talking about a dimension of 100 mm, that these are basically these members here, that is angle members. And one is 150 mm, it is approximately 0.323. So 0.215 for 100 mm and 0.323 for the 150 mm. So we can click on the elevation here. So on all of these members which are in 100 mm in dimension, we have to apply 0.215 kilonewton per running meter. So on all of these members, we have to apply 0.215 kN per running meter. So now it is applied, and for the 150 mm, it is 0.323. That is for these members. Similarly, when we are talking about this particular member, that is these, yeah, it on this member, it is already applied. Yeah, so now we can click on just escape option. Again, we can go to the elevation view, elevation along grid 1 and apply. So now in all of these members, we can see that the loading is applied. Only on this member it is pending for 310. So what we can do is that we can have conservative apply this loading itself, that is 0.774. So we can select this member and apply 0.774 kN per running meter. So now this is basically the loading for grid 1. But the thing is that we have this particular grid again, on the complete grid that we are considering. Now the second option is that we have to consider the shielding effect also. So shielding effect, obviously it shall be different when we're talking about this particular member, because it shall be shielded with the, we can say, we can just go to the display and deform shape. And for as of now, we can just simply switch off the section so that I can explain you what we are trying to convey. So the thing is that when wind shall be striking here on this particular member, it is not that this shall form a complete barrier and this particular member, it shall be completely isolated from the effects of the wind. Obviously there shall be some shielding, that is let us say if we are having a value of 1 here, on this particular frame it can get decreased to 0.3, 0.4 or 0.2 also. Similarly, for this particular column member, again we do have some shielding for this particular member. So the shielding effect multiplier that can be considered from the code itself. But the thing is that if we are trying to apply the wind load on all of these members here, we have to consider the shielding effect on this particular grid number 2. So if we switch on to grid number 2, so we have to apply wind load on these members also. So this was the basically the multiple open frames concept. So shielding factor KSH for multiple frames, it basically depends on the effective solidity ratio, that is delta E. So if we are talking about the frame spacing ratio less than or equal to 0.2, for the effective solidity ratio greater than 0.4, the value comes out to be 0.2. So in many of the cases that I have handled, the value in between comes out to be 0.2 and 0.4. So in our case, we can, conservatively assume it as 0.3, although it is always recommended to exactly calculate the frame spacing ratio and effective calculate the effective solidity ratio. But it shall decrease the length, it shall increase the length of the lecture by much span. But the thing is that you can just simply calculate that is not a very difficult thing. Solidity ratio means that, let us say we do have this particular two members, and this is the whole cross-section dimension. So we multiply or find out or add this particular dimension and divide it with this particular total dimension to find out the effective solidity ratio. So we can just simply the values that we have calculated here, we can just simply multiply all of these values with 0.3 to find out the values that we have to apply on the grid number 2. So we can just simply open the calculator first of all. So 0.774 multiplied with 0.3 gives us 0.233. The second value comes out to be 0.495 multiplied with 0.3 gives us 0.149. The next value, it comes out to be 0.129. This value comes out to be approximately 0.065. And this value comes out to be 0.323 multiplied with 0.3 gives us 0.097. So for the grid number 2, we can apply these values. So for 360 mm dimension, we can apply 0.233. Again, we can switch on the sections. Assign, frame loads and distributed. We can apply 0.233 global Y, WLY serviceability and apply. So now we have applied the value of 0.233 on all of these members. After that, the second dimension is 230 mm. That is the columns itself. So for that, we have to apply 0.149. So we can select all of these vertical members here. We can enter value of 0.149. So now it is also applied. Third value is for 200 mm. That is the bracing members. The value comes out to be 0.129. So we can select both of these members. We can enter the value of 0.129. After that, we do have to apply the wind load on these members, that is 100 and 150. So for 100 mm, it is 0.065 and for 150, it is 0.097. So 0.065. And we can click on apply and 0.097 for 150 mm members. So now we have applied the wind load on all of these members for the, we can say, along this particular Y direction, considering the shielding effect also, considering the cross-sectional area dimensions. So now we can say that we have applied the wind load serviceability for one axis. And similarly, we can repeat the whole process for the ultimate wind load case also. So for ultimate wind load case, instead of, we can say, 48.23, we do have 72.8. So we can, click on, the CSH plugin, we can take it as 1.54. CDIN is basically 1. So the value comes out to be 4.898 kPa. So the similar exercise that can be repeated for all of these numbers here. So 1.64 again, that can be multiplied with 0.3. So 1.764 multiplied with 0.3 gives us 0.53. 1.127 multiplied with 0.3 gives us 0.338. 0.98 multiplied with 0.3 gives us 0.294. 0.489 multiplied with 0.3 gives us 0.147. 0.734 multiplied with 0.3 gives us 0.221. So for the front axis, again we have to repeat the whole process for WLY ultimate. So the values are for 360 mm 1.764. So we can open the elevation along grid 1 and we can select WLY ultimate, and this value that has to be 1.764. 1.764 kilonewton per running meter. So we can select all of these members here. 1.764 and apply. Okay. And the second value that we do need to apply is 0.338 for the columns. So all of these values has to be 0. Sorry, it shall be 1.127. 1.127. So now the wind load is applied here also. The next shall be 0.98 for 200 mm dimension. This is the 200 mm dimension. So here we have to apply 0.98. After that we apply on the bracing members here. So that has to be 0.489 for 100 mm. That is this dimension, and 0.734 for 150 mm. So we can enter 0.489 for 100 mm and select all of these 100 mm dimensions here, and 0.734 for 150 mm. And again for elevation along grid 2, we have to consider the let us say shielding multiplier of 0.3. Again we have to repeat the whole exercise. So for the horizontal members, it has to be 0.53. So we can select all of the beam members here and enter it as 0.53. For the column member, it has to be 0.338. So we can enter 0.338 and select all the column members here. For the 200 mm dimension, it has to be 0.294. We can take it as 0.294 kN per running meter. For 100 mm and 150 mm, it shall be 0.147, 0.221. For these members, it shall be 0.147. And for these members, it shall be 0.221. Okay, so now the loading has been applied and all the, loading it has been considered. Yeah. So for ultimate and for along this particular direction, we have applied all kinds of loading that are applicable as per the code. Now we can apply the loading along the x direction also. So the similarly exercise has to be repeated for all of these members here. The only difference is that we do not like there must be pipes that are getting rested here, and along this particular direction the wind loading is very negligible because of the very small cross section area, so we can ignore that. So that is why for this particular direction, that is loading along x, we only consider the loading on the structural steel members itself as per the code. So in here, we do need to understand that this particular dimension of the column, that is approximately 530 mm. So that contributes a major factor in the wind load calculation or in the wind load final values. So accordingly, we have to consider the UDL on all of these members here like this, and on the beams also like this, and on the columns also like this again. So this wind loading, obviously, that can be calculated along x direction. It shall be called the wind axis itself. So considering that 48.23, that is again the serviceability load case, the value comes out to be 2.233 kPa. And for surface dimension of 530 mm, we can take it as 1.184. For 360 mm, we can take it as 0.804. For 229 mm dimension, we can take it as 0.648. And for 250 mm, we can take it as 0.559. And similarly, we can repeat the same exercise for the ultimate load case for 5.087 kPa, and we can apply these values on the members again. Now the again the concept comes that if we're talking about the wind load along this particular direction from this point along this axis, again there shall be a little bit shielding on the we can say wind, but it won't be that high, because if you're talking about a distance from this member to this member, it is approximately 6 meters, and let us say if we're talking about from this member to this member, it is again 12 meters. So shielding won't be that much applicable. So what I usually do is that I take it on the conservative side itself, that we can assume it here that on all of these members, because there is not as much shielding on the we can say structural steel members, so we can take the full contribution. But for these members, because ultimately wind shall be traveling here and wind shall be striking on these members, let me show this in the plan again. Yeah, let us say on these members here, where the wind is, striking, there shall be shielding, because these two members are very closely spaced with each other. So we can consider the shielding effect multiplier for these members, but not for these members. Again, that is my point of view, which can be, you know, have some other engineer may have different opinion, but I do, consider this result to be considered on somewhat conservative side. So that is how, we can apply the wind load along x direction also. So considering all of these members here, these are the like members which are having approximately 530 mm dimension. So considering WLX and serviceability, and again, we have not taken the all stories option, or what we can do is that uh, we can just select all of these arrangement first of all. So the ideal approach here is that either we can click on the all stories option, go to the plan view, and select all of these column members again. and apply the column UDL for serviceability. That is approximately 1.184 for the serviceability. So we can apply 1.184 kN per running meter. Direction shall be global X. So now we can see that we have applied the wind load along this particular direction. And if we're talking about the ultimate load case, that is approximately 2.696. So again, we can select a WLX ultimate, and again, we can select all of these column members here. We do need to ensure that all storage options are selected. So we can apply 2.696 kN per running meter. So now this is also applied, and after that, if we're talking about the next dimension, that is approximately 360 mm. So for 360 mm, it is 0.804 and 1.832. So this is basically the dimension that we are right now talking about. That is 360 mm dimension. And if we're talking about WLX, first of all, we are talking about WLX serviceability. So we can enter 0.804 and we can apply the loading on all of these 360 mm members here. First of all, on the portal frames itself, the main portal frames, and we can consider the shielding effect multiplier on the like smaller sizes members here. So considering that, we can multiply it with 0.3. So the value comes out to be 0.24. So we can apply the UDL on these members. We can increase it a little bit higher. Let us say we conservatively want to apply 0.3 kN per running meter here. Because ultimately, again, we have to go into detailed calculation, which I think is not required at this stage. Because we are right now only discussing or understanding the concept here. So now we have considered the shielding effect multiplier on all of these members and applied the appropriate wind load. So again, the next dimension comes out to be 229 mm. And if we're talking about the 229 mm, that is the column size itself. And if you're talking about a 250 mm dimension, that is approximately 0.559. Let us just go to the 3D view again. Go to the display and undeformed shape. So as of now, we have applied the uniformly distributed load for the columns also and for these beams also. So as of now, it is covered. For this particular member, it was calculated, that is 250 and 360. Yeah. So for 250 mm dimension, it is approximately 0.559. So for WLX serviceability, we can apply it as 0.559 kN per running meter. Yeah. So with that, concept, you can apply the wind load. And for the ultimate stresses for the 250 mm dimension, it is 1.272. So here we can apply 1.272 and we can select WLX ultimate. So we can select both of these members here and apply 1.272. So now we can see that we have applied the loading on all of these members here. Yeah, but I think the loading is missing on these members. WLX ultimate. Yeah. So what we need to do is that we do need to go to the plan view again, level 2. And for 360 mm dimension, for the ultimate, it is approximately 1.832. So we can select all of these members here and enter 1.832. That is the beam members. So select all of these members and apply the UDL of 1.832. Yeah, but thing is that, either we can proceed with that approach, or what we can do is that on these members, that is the main portal frame members, we can apply the full UDL, that is 1.832 kN per running meter. And on the intermediate members, we can consider shielding effect multiplier, that is 1.832 multiplied by 0.3 gives us approximately 0.54 something. We can conservatively take it as 0.6. So we can apply the UDL of 0.6 kN per running meter on all of these members here. Yeah, so now this value comes out to be 0.6. And these are the values on the main portal frames, which gives us 1.832. So now we can say that the wind load has been completely applied on the structural steel pipe rack, considering the open members, considering the shielding multipliers, considering the serviceability and the ultimate, considering the aerodynamic shape factors also. So I hope that this exercise is now clear to you that how we can apply the wind load. But the thing is that this whole exercise shall be, iterative. That is, after applying this wind load, if some of the members are failing in the design, we again have to repeat the whole exercise by selecting the higher size members. By selecting the higher size members, the wind load again increases. So that is how, we can calculate and we can apply the wind load on the structural steel members.